Good morning. I welcome you to the session of IC engine and gas turbine, and today we will discuss about the cooling of engine. In fact, if we try to recall that in the last lecture we have discussed about the generation of energy in the form of heat. So, the energy which is being converted from the one form to the other form, that is from the chemical energy which is being converted into the other form of energy in the form of heat because of the combustion. And now the heat which is being developed we need to utilize, but we have seen that all the heat cannot be utilized and 30 to 45% heat is being utilized to create thrust on the piston face, while remaining heat is being lost in different other forms. And we have seen that we need to cool down, rather we need to reduce the temperature of the engine cylinder, and we have critically discussed that heat which is being developed should not be too high, so that the lubrication system will start malfunctioning. So, in order to prevent that, also to prevent some other parts of the engine from different other undesirable phenomenon like generation of crack and other things, engine should be cooled. And we will discuss today that there are two different ways by which the engine temperature can be reduced. So, the engine temperature should be reduced essentially to prevent the lubrication system and also the other different other parts of the engine. On the other hand, the temperature should not be reduced drastically, so that the efficiency of the engine will be reduced. So, today we will discuss about two different cooling systems of the internal combustion engines, that is air cooled and liquid cooled engine. But before I go to discuss about the cooling system, I would like to briefly discuss about the two important parameters that we have introduced but we did not define, that is the octane number and Cetane number. Why these two parameters are important and why these two parameters are coming into the picture essentially in the context of IC engine operation. So, today we will discuss about two important parameters, that is octane number and Cetane number. So, in this context I would like to discuss that these two numbers are important in the context of the internal combustion engine operation. To be precise, the self ignition characteristics of the internal combustion engine. If we try to recall that for the SI engines we have seen the existence of one external agent, that is spark plug. The spark plug is used to ignite the charge for the initiation of the combustion. But if we now look into if we now recall the CI engine combustion process, where we have seen that the thermodynamic state of the charge, to be precise thermodynamic state of the compressed air at the end of the compression stroke is used to initiate combustion, and there is no requirement of any external agent like spark plug. So, whether a particular fuel will be in a position to self ignite, that means that is what we have seen in the context of CI engine operation. So, the fuel that are used for the CI engines should have sufficient, I can say very good self ignition characteristics. That means at the end of the compression stroke the temperature inside the cylinder will be good enough to ignite the fuel. If we tell it in another way, that means the moment when fuel is injected into the cylinder towards the end of the compression stroke, the thermodynamic state, pressure and temperature, in particular temperature of the compressed air, now in a position to ignite the fuel. That means the fuel will have self ignition characteristics. So, when we are going to define these two important parameters, we need to know what is self ignition characteristics. So, I am writing now the self ignition characteristics. So, the definition is the I can say that, so that means the temperature inside the cylinder, inside the combustion chamber is very high. Now, what is the value of that high level temperature? This is qualitative. So, we are telling that temperature should be reached at a value. Now, that temperature will be in a position for the self ignition of the fuel which is being sprayed into the combustion chamber. So, this is again qualitative. So, we need to define what will be the temperature limit at the end of the compression stroke of the compressed air, and that temperature will be able to ignite, that temperature will be able to self ignite the fuel which is being sprayed for a particular fuel which is being sprayed. So, depending upon the fuel characteristics, we need to know what will be the self ignition temperature, and that is and above which the entire combustion will start. So, I can just schematically tell you that so this is BDC, this is TDC, and cylinder movement is between these 2 points. Now, when fuel is injected, fuel is sprayed, fuel is injected into the cylinder. So, at the end of the compression stroke, when piston is approaching the TDC, now that time temperature will be good enough or above the self ignition temperature of the fuel itself, and that is which is very important to ensure that the combustion for the SI engine will be completed. So, what is the self ignition characteristics? The temperature above which fuel will self ignite and we do not require any external agent. So, that means why it is important, that is why it is important to know. So, when if we try to recall the combustion of the CI engine, that that fuel ignition fuel spraying starts when piston is 10 degree before TDC, and that time the fuel which is being sprayed during the first phase, and by that time when piston reaches at TDC, the first phase fuel which is being sprayed will be in a position to ignite, and when a particular fuel ignite in the combustion chamber, there will be a that is called chain reaction. So, the one fuel will ignite, because of this ignition another the temperature will be developed that will try to ignite the adjacent fuel, and in this way the total combustion will take part. So, we need although the finite amount of time, although the time is a very small fraction of the second. So, but we need this finite amount of time, and that is known as delay, and that is what we have seen, that delay period is essentially is now the combination of physical delay plus chemical delay. So, the total delay period we need to ensure that after which the entire we can see the combustion has started, and again combustion has started, the manifestation of the combustion is the appearance of a visible flame qualitatively, but if we need to know quantitatively, that is what we need to measure the pressure. So, the self ignition characteristic is that the temperature above which the fuel, if it is or fuel plus air mixture, will self ignite without the need of an external agent. Like spark plug. So, this is very important, that fuel we need to ensure that the temperature at the end of the compression stroke should be above that level, and that level we need to somehow ensure that will be there because of the compression if it is the CI engine. So, this is very important. I can tell that this is the basic, this is this is the basic principle of CI engine ignition. That means we need to ensure the temperature at the end of the compression stroke should be above that temperature, and that is known as the self ignition temperature. Or SIT in short. So, the temperature, this is the basic principle of the CI engine, because for the SI engine we have an external agent spark plug. So, I mean this is not very important, but at least we should know this, and keeping that in mind, a very frequent question is, if we use diesel for the SI engine and vice versa, then what will happen. So, I will try to address that question, but for the time being you should know for that, but for the CI engines, the temperature at the end of the compression stroke should be above the self ignition characteristics, the self ignition temperature of the fuel which is being used, and that is very important to know. Why this is important? So, if we know the self ignition temperature of a particular fuel, and if we know that the self ignition temperature of the particular fuel is not very high, then what will happen? If we use that particular fuel for the SI engine, then what will happen? So, I mean, if we use a particular fuel where the self ignition temperature is not very high for the SI engine, self ignition will occur, and because of the self ignition the rise in pressure will be drastic, and that will lead to I can say damage of different parts of the internal combustion engine, or sometimes it may leads to damage of the internal combustion engine as a whole. So, what I would like to say that if we use a particular fuel for the SI engine, and if that fuel is having self ignition temperature which is not very high, so when if that particular fuel is now being supplied with the mixture of air, that is air fuel mixture, and piston is coming up towards the TDC, what will happen? The rise in temperature will allow the fuel to self ignite. If it happens, there will be rise in pressure, a pressure pulse will be created, and that will leads to audible noise, and that will also known as knock or ping. Not only that high pressure pulse can leads to damage of the different parts of the internal combustion engine, or quite often they also leads to the complete damage of the internal combustion engine. So, this is very important to know. So, this is the self ignition temperature. Now, as I said that if I now try to draw the time versus SIT, that is self ignition characteristics. So, this is true that there will be, if we consider particular fuel. So, if we consider particular fuel, we know that for that particular fuel self ignition temperature is fixed. So, SIT is fixed, and this is the temperature level. So, this is the temperature. So, I can say this is temperature, not SIT, this is temperature. So, we know that for that particular fuel self ignition temperature is this. Now, what will happen if we now try to bring the piston from BDC to TDC? It will take some time, and with time what will happen? Time will progress, and as a result of which the temperature inside the combustion cylinder of the air will increase. If the rise in temperature at the end of the compression stroke, almost at the end of the compression stroke, is below the self ignition temperature, then there won't be any combustion. So, that is, if the self ignition temperature, if the temperature rise of the air is less than the self ignition temperature of the fuel which is being sprayed into the cylinder, so what we can see, we can rise the temperature of the air because of the compression process, and towards the end of the compression process we are now igniting fuel, maybe here we are igniting fuel, but what we can see, after the end of the compression stroke the temperature will be almost fixed if there is no any combustion. So, the temperature will be constant. But what we can see, since the rise in temperature is less than the self ignition temperature, there will not be any combustion. But if that means we need to ensure that the rise in temperature should be always above than the self ignition temperature. So, rise in temperature should be higher than the self ignition temperature. Now, another case, if we consider the rise in temperature at the end of the compression stroke is high, then say this is the case, then this is obvious that fuel will self ignite. So, the fuel which is being sprayed into the cylinder will self ignite, because at the end of the compression stroke temperature inside the cylinder is higher than the self ignition temperature of that particular fuel, right. Now, what we can see, that immediately when fuel is being supplied into the cylinder, maybe this point is at the end of the compression stroke, temperature is higher and we are injecting fuel. So, the moment when we start injecting fuel, the entire combustion won't be completed. It will take some finite amount of time, although the time is a very small fraction of the second, but even then we need to say, rather we should say, this is finite amount of time, and this time is known as ignition delay. So, maybe we have started injecting fuel, and the amount of fuel that will be supplied, that will be sprayed into the cylinder per stroke should not be, rather it is very difficult to ensure that the amount of fuel that we need to supply per stroke will be supplied momentarily. So, because of the nozzle is a mechanical part and it will take some finite amount of time, that is physical delay. So, the amount of fuel which we intend to supply per stroke should not be supplied or very difficult to supply momentarily, it will take some finite amount of time, together with the fact that when we start injecting fuel, the first part of the fuel will ignite, it will now try to ignite the adjacent layer in such a way that is just like a chain reaction, and it will take some finite amount of time, and that time will depend upon the chemical characteristics of the fuel. So, these two delay, that is physical delay, because which is associated largely with the nozzle performance. Second is the chemical delay, which is largely associated with the chemical characteristics of the fuel. We need some amount of time, and then when the this delay period is over, that is a very small fraction of a second, and then entire combustion will be completed, and there will be significant rise in temperature, and that is why this period is known as delay period. So, this is known as delay period. So, this delay period, sometimes it is known as ignition delay. This delay has two defined parts, one is physical delay, another is chemical delay, right. Now, if we somehow can ensure that the temperature at the end of the compression stroke should be higher than, rather I can say which is relatively second case, if we consider the rise in temperature at the end of the compression stroke, which is sufficiently higher than the self ignition temperature, then what will happen? We can reduce the ignition delay period. So, now it will start like this. So, the ignition delay period will reduce if we, so the ignition delay is continuously reducing. That means, if we can ensure that the end of the compression stroke, the rise in temperature or the temperature of the compressed air is sufficiently higher than the self ignition temperature of the fuel which is being sprayed, then we can reduce the delay period and we can accelerate the combustion process. So, this is all about the self ignition temperature. Now, we should try to define the definition of the Cetane number and octane number. What is octane number then? So, octane number So, we have understood that what is octane number. So, we have understood the self ignition characteristics and why it is important. Octane number, I am writing the definition, which is again a fuel property that indicates how well, how good a fuel will self ignite or not. So, this is the case, how good a fuel will self ignite or not. So, basically, and this is known as octane number, and this is again numerical scale. So, basically we need to compare, we have defined fuel, as I said the fuel is a family of hydrocarbon. Now, we need to have a scale and we need to compare the fuel with this standard or numerical scale. So, this is essentially a numerical scale and which is generated by comparing self ignition characteristics of the fuel to that of the standard fuel. Fuels in a specific test engine, in a specific, I can say, test engine, and at specific operating conditions. That means we need to compare a particular fuel with a standard fuel. So, it is just like a calibration. So, we need to compare with whom, with a numerical scale. So, and that is that numerical scale that is generated by comparing the self ignition characteristics of two different fuels, and that is again experimental observation, and this experiment is done in a specific test engine, experiment is done in a specific test engine at a specific operating condition. So, now I can write this octane number to standard fuels are N-heptane, whose octane number, so this is octane number. I am now trying to discuss about the numerical scale. This is known as octane number. N-heptane octane number is 0 and isooctane whose octane number is 100. So, we know that these two standard fuels are used. We know a priori the octane number of these two standard fuels. For N-heptane it is 0, for isooctane it is 100. So, and we can now try to if we compare any particular fuel with these two standard fuels, we can tell what will be the octane number. One important point is that higher the octane number, the fuel will have less tendency to ignite, right. So, higher the octane number, fuel will have less tendency to self ignite. That is very important, and that is why engines which are having two, high compression ratio, high shear and low shear. So, this shear is the compression ratio. For the low shear, the engines which are having low compression ratio, those engines can use fuels which are having less octane number or lower octane number. And the higher compression ratio engines, the engines which are having higher compression ratios, these engines will use fuel which is having higher octane number. So, this is the indication. So, with this, next we move to see what is the definition of C10 number. C10 number or Cn, what is that? So, we have discussed about the self ignition characteristics. In the context of that, we have defined one important number which is largely used for the SI engine, characteristics fuel. So, now the octane number is an indication whether a particular fuel will self ignite or not. Now, C10 number is another important number which is also important to know the definition at least. So, this number is very important in the context of compression ignition engine. So, in CI engines, self ignition is necessary. That is what we have understood till now, that for the compression ignition engine there is no any external agent, and the thermodynamic state, rather temperature at the end of the compression stroke is used to ignite the fuel which is being sprayed. So, this is an important for the CI engine. Which is important? Self ignition characteristics, self ignition is important. Now, accordingly we need to know, if we know the compression ratio, we need to select a particular fuel for the operation of the CI engine which will self ignite, and which will self ignite at a proper time, and proper time of this total cycle. I mean, we are spraying fuel towards the end of the compression stroke. So, maybe we are fuel piece started spraying towards the end of the compression stroke, but if it happens that fuel will ignite when piston is coming back from TDC, that is not desirable. That means the CI engine self ignition is important, very necessary, and the properties of the fuel will be selected in such a way that it will self ignite at a proper time. Now, that means, and the fuel will self ignite at a proper time. So, this is very important for the CI engine. Now, at least we need to know which fuel will self ignite at a proper time. So, that means we need to know, at least we should have knowledge about the control the ignition delay. That means, maybe we are igniting fuel towards the end of the compression stroke, but the self ignition temperature of the fuel is we did not check, and the fuel which is supplied will self ignite when piston is travelling back from TDC, or sometimes it also happen that the fuel will not self ignite. So, this is very important for the CI engine ignition combustion, that fuel which will be supplied will self ignite at a proper time. So, this, whether the fuel will self ignite at a proper time or not, this requires the control an ignition delay time of the fuel. So, if we know the control and ignition delay, if there is ignition delay will be there. So, what is the delay period time, what is the delay time, and whether we can control the delay time or not. So, these two important points we need to know before we go to select a particular fuel for the CI engine combustion. And the parameter which the property I can write that quantifies these characteristics is called the Sitten number. So, Sitten number is again a number which is used to quantify the characteristics of the fuel, whether the fuel will self ignite or not, and whether the fuel will self ignite at a proper time or not. And this is again a numerical scale. So, I am writing like octane number, Sitten number is also a numerical scale which is generated comparing two standard fuels at in a certain specific test engine and at a specific operating condition. So, Sitten number of the fuel is again numerical range and which is generated. The scale is generated by comparing two standard fuels in a given in a specific test engine and at a specific condition. Now, this is nothing but percentage of N Sitten. This is just numerical scale I am writing N Sitten plus 15% of 0.5 times into percent of hexamethyl nonane. So, this is hexamethyl nonane and which is chemical formula is C12H34 and N Sitten which is having chemical formula C6H34. So, this is having Sitten number 100 and this is having Sitten number 15. So, this is the chemical numerical scale generated, but important thing to note that what will happen if Sitten number is larger or Sitten number is lesser. Larger and lesser, I mean relatively larger, relatively lesser, that means if the Sitten number is too high or too less, then what will be the consequence this number on the ignition delay, and that is what we need to know. So, if that is Sitten number of a particular fuel is obtained by comparing the ignition delay of a mixture blend of two reference fuels, and that is what we have mentioned. So, higher the Sitten number, the larger, rather I can say larger the Sitten number, shorter will be the ignition delay and quicker will the fuel will ignite very quick, and low the Sitten number will have larger ignition delay. So, that means I am writing in the next slide that Sitten number, that is larger value, sorry I can say then shorter ignition delay, shorter ID, that is ignition delay, that is fuel will self ignite quickly, and smaller Ceten number, that is I can say longer ignition delay, and definitely fuel will not be in a position to self ignite quickly. So, this is these two important parameters which are very important to know in at least to predict the ignition delay period for the internal combustion engine, while the octane number is very important to know whether the fuel will self ignite or not. So, these are the very important two important points. Now, with this we need to know what are the cooling system. So, this cooling system we have discussed about that the combustion reaction is exothermic reaction, and we are the reaction leads to the development of energy in the form of heat, and all the heat is not getting converted into the work equally, and some I can say substantial amount of heat is being dissipated definitely through different parts of the engine. A small portion is now dissipated by the coolant which is being supplied to cool down the engine cylinder, and substantial part is being lost during exhaust blowdown, and there are other different parts of the energy which is heat which is energy, and that is again converted to run the auxiliary systems of the internal combustion engine, that is the parasitic loads. So, this internal combustion engine cooling system can be broadly classified into two different categories, that is air cooled engine and other one is the water cooled engine. Air cooled engine and water cooled engine. Water, if you use water as a coolant, we have seen from our heat transfer knowledge that water is the fluid which is having very good characteristics which are very important for the as a coolant. So, water, the thermodynamic properties, I can say the water is having a few important properties which make water a very good coolant, but sometimes we cannot use water as a coolant for the internal combustion engine, at least in the northern climate regions, because where temperature will be less than 0. So, if we use water as a coolant, then we will have a few disadvantageous feature. Advantageous feature, we know that as I said that water is having a few important properties which make water as a very good coolant, but these important properties become I can say the unimportant if we use water as a coolant in the northern climate regions for the internal combustion engine operation. So, on the other hand, if we use air cooling is also an important, but air cooling also having a few disadvantageous feature. So, if we use air, and then what are the disadvantageous feature we need to know, but at least the problem won't be there which is associated with the use of water as a coolant in the northern climate region. So, now I would like to just tell you that the heat which is being generated, so heat which is being generated, and that is due to burning of fuel, and 30% of that heat is transformed by the engine in the form of work, 30 to 35% has to be removed by the cooling system, in the form of work, and the remaining by is lost by exhaust and lubrication system. Right. So, this is the thing, and as I said that 30% is transformed by the engine in the form of work, 30 to 35% has to be removed by the cooling system, and that is why cooling system is important for the internal combustion engine, and remaining is by exhaust and the lubrication system. Now, question is, this 30 to 35% heat has to be removed by the cooling system, but if we do not have this cooling system properly, then what will happen? That means this heat, this amount of heat which is substantial, and this heat we need to remove by cooling system. If we do not remove this heat, then what will happen? The lubricating system will start malfunctioning, property of the lubricating oil will be destroyed, the heat also might leads to crack in the cylinder wall, thermal crack, and also damage of different other mechanical parts like valves and the piston wall. So, that is why this amount of heat we need to remove. When we talk about removal of heat from the internal combustion engine, there are two ways, and that is what I have written over here: air cooled and the water cooled. Now, air cooled engine, I mean that is liquid cooled and air cooled. So, if we first talk about the air cooled engine, that is air cooling. We know from our heat transfer knowledge that Q, that is what the heat flux that we need to remove, that is proportional to the area. So, if we increase the surface area, we can dissipate more number of heat, and that is why the engines are sometimes having extended surface. From the engine wall we have extended surface, that is fin, that is what we have studied from our basic heat transfer course, conductive heat transport. So, the engine walls are having projected part of different shapes, and research is continuously going on. In fact, people have done research in on this topic, and the extended part in extended portions are used only to increase the surface area, so that the if it is air cooled engine, then this surface will be in contact with the air and we can dissipate larger amount of heat. Now, this air cooled engine is also having a few disadvantages and advantageous feature. What are those? First of all, advantage is lighter weight, low cost, no failure of cooling system, and if we use water as a coolant, and as I said, in the northern climate regions very difficult, below 0 degree it will start freezing, and also the boiling temperature of the water is also fixed. So, that problem is not there with the air if we use as a coolant. So, that is known as no engine freeze offs, but a few disadvantages also there. So, lighter weight, low cost means if we use water as a coolant, again we need to liquid is having inertia. So, we need to transfer water from one place to the engine part, and then again we need to take the hot water from the engine to the one device, so that we will have kind of cooling over there, and again we can reuse that water. So, for that we need to have a complete cooling system where we need to have pump. But if we use air, is having less inertia, as such the movement of the engine cylinder is, I mean I can say allowing a portion of the air to be drawn inside the engine and that air. So, the forward movement of the engine is the movement itself is responsible for some amount of air to be drawn into the engine cylinder. So, I mean we do not require any kind of other parts like pumps and all those things, but the disadvantage is that it is less efficient, Number 2 is or noisier. So, these things are there, but and also the less efficient means it is not as good as the air is not having properties which are I mean as I said, water as a coolant is having a few properties which makes water as a very good coolant, specific heat and other things. So, if we compare that aspects, then of course air is having a few disadvantageous feature. Now, if we use water as a coolant, in that case again I am telling, if we use water as a coolant, then water which will take some amount of heat from the engine cylinder, that heated water again you need to cool down. So, the heated water will be taken in another part, and that in that part water will be stored, and there again we need to cool down the water so that the water can be reused again. So, if we use water as a coolant, again you need to have another I can say another heat exchanging heat exchanger where the heated water can be cooled down. So, if we use water as a coolant, this is another important problem. That means system will be very bulky and it will be costly. That means we need to pump water from that auxiliary heat exchanging portion to the engine cylinder. So, what heated water is taken from the engine cylinder, it is now stored in another part of the engine where heated water is cooled down by providing air, and again that cold water is taken into the cylinder. So, this system needs a few mechanical equipments, that is pumps and conveyor, all those things, a piping line, all those things. So, this makes this equipment makes the system very costly. Not only that, water is having a few important properties, at the same time it is having quite quite a few problems if we use water as a coolant. That is, it promotes rusting and corrosion of the piping line and the different parts of the engine cylinder. And not only that, water cannot be used as a coolant in the northern climate region where temperature will be less than 0 degree. But as I said, although water is having this disadvantageous feature, but the properties, specific heat makes water as a very good coolant, and that is why water is used as a coolant. And for that one external agent, that is called antifreeze C2H6O2, that is ethylene glycol. Which is mixed. This ethylene glycol is a very good, this is additive, and it promotes rust, rather I can say it acts as a rust inhibitor, and also a lubricant for water pump. So, if we use ethylene glycol as an additive, we need to mix water with this ethylene glycol. If we mix ethylene glycol, it will act as a rust inhibitor. Not only that, as I said that we need to have an auxiliary pump, and that pump will be responsible to transfer water from that secondary heat exchanger to the engine cylinder, and this ethylene glycol will now act as a lubricant for the water pump. Not only that, this ethylene glycol, that is what is very important, that if we use water again as a coolant for the engine in the northern climate region, this ethylene glycol lowers the freezing temperature and raises the boiling temperature. So, that means if we use water as a coolant, there are a few disadvantageous features. That means it should be costly. We need to have another secondary heat exchanger to cool down the water using air, and also we need to have pipeline. But this secondary system makes the system very costly. But other hand, the big important property of the water is the specific heat. So, we can use water as a coolant, and for that we need to add additive, that is ethylene glycol. It will make as a rust inhibitor, and also it will act as a lubrication for the water pump. And the addition of ethylene glycol will lowers the freezing temperature and also increase the boiling temperature, and it will make water as a perfect coolant for the internal combustion engine. So, to summarize today's discussion, we have discussed about two important parameters, two important numbers which are very responsible, which are important to know about the self ignition characteristics of the fuel and how well a fuel will self ignite or not. And then we have defined these two parameters, and we have tried to understand the numerical scale of these two parameters. And then we have discussed about the cooling system. There are two important cooling systems are there, that is the water cool and air cool. If we use air cooled engine, of course we do not require any external another additional system. The forward movement of the engine will allow air to be drawn into the cylinder, and of course that is there, but although the forward part of the engine cylinder will be in contact with the air, and we can have heat transfer from there, but the rear part of the engine cylinder won't be able to in contact with the air, as a result of which we will have dissimilar heat transfer from the engine cylinder. But the air, if we use as a coolant, then a few advantageous features are there. On the other hand, if we use water as a coolant, we have seen that there will be a few one important advantage is that specific heat, and we can use water as a very good coolant, but at the same time we are having a few disadvantageous feature. So, to remove these disadvantageous feature, you can mix ethylene glycol as an additive, and which will act as a rust inhibitor, and also it will be the lubrication for the water pump. So, and not only that, the ethylene glycol will lower the freezing temperature, and it will increase the boiling temperature, which is good for the water, and we can use water in places where temperature is less than 0 degree Celsius temperature and greater than 100 degree Celsius temperature. So, with this I stop my discussion today, and I will continue my discussion in the next class. Thank you.